Welcome, aviation enthusiasts. I'm your flight instructor, and in today's learning guide, we're going on a journey from the raw aerodynamic physics of a propeller blade straight into the pilot seat of an advanced aircraft. We're going to take all that complex mechanical theory from your training manuals and translate it into intuitive, actionable knowledge. Our goal: true cockpit mastery. Here is our flight plan for this explainer. 1. How propellers create thrust. 2. Propeller pitch and slippage. 3. Inside the governor system. 4. Cockpit controls engine stress. And 5. Handling propeller malfunctions. Let's dive right in. Section 1. How propellers create thrust. To really get this, we need to step outside the aircraft. A propeller is essentially just a pair of specialized, rotating airfoils hooked up to a central hub. Just like a wing produces lift to keep us in the sky, a prop uses those exact same aerodynamics to pull us forward. But think about the cross-section of the blade for a second. You'll notice it's twisted. Why? Well, because the tip of the blade travels a much greater distance than the root near the hub in the exact same amount of time. So the inner prop operates at a high angle of attack with low velocity, while the outer prop has a low angle of attack with high velocity. This is a brilliant piece of design because it creates uniform thrust all the way along the blade. Literally, if it weren't twisted like this, the structural load on the outer sections would be so high, the blade would just fail. Now, the absolute key here is how the air interacts with this twisted shape. As laminar airflow, that's the air sticking to and following the curve, moves over the blade's surface, it creates a void, a low pressure area on the front upper surface of the blade. The high pressure from behind naturally wants to rush in and fill that low pressure void. But, well, the propeller is in the way. So the high pressure literally pushes the propeller forward. And remember Newton's law, every action has an equal and opposite reaction. That is exactly why you feel that massive rush of downwash when you're sitting in the run-up area right behind the prop. So when we put it all together, think of the overall motion just like driving a giant corkscrew into a wall. The blade's angle is actively pulling the airplane forward through the air. And the path it takes, it's based on a combination of your forward velocity and your rotational velocity. You are quite literally carving a spiral path through the sky. Section 2. Propeller pitch and slippage. Okay, so most basic trainers have fixed pitch propellers, right? That's where the manufacturer locks in a specific blade angle. You can't change it in flight. To understand how efficient or inefficient this is, we have to talk about two types of pitch. Geometric pitch is the theoretical distance the prop would move forward in one single revolution if it were spinning through a solid medium. Just imagine it carving through a giant block of butter or tofu. Effective pitch, on the other hand, is the actual real-world distance it moves forward through the air in one revolution. The lost distance between that theoretical geometric pitch and the actual effective pitch is what we call slippage. It's exactly like a swimmer's hands, or say a canoe paddle, slipping backward through the water as they push. Because air is a fluid, we are always going to have slippage. This dictates our overall propeller efficiency, which usually ends up being somewhere between 50 and 87%, depending on your air density and blade angle. So manufacturers have to make some serious trade-offs here. A climb propeller, like the one you'd find on a Cessna S model, uses a low blade angle and a high RPM. This converts maximum fuel into takeoff thrust, keeping things highly efficient at low speeds. But a cruise propeller, like on a Cessna R model, uses a high blade angle and lower RPM to grab a massive chunk of air per revolution. This saves fuel and wear and tear at high speeds, but it's super inefficient during a climb because you need way more RPM to move the same amount of air. To solve this exact problem, advanced aircraft, like the Piper Arrow, use a constant speed propeller. This is a real name changer. It acts as an adjustable pitch system that automatically keeps the blade angle optimized. By constantly changing the geometric pitch mid-flight, it minimizes slippage and maximizes efficiency in practically every single flight condition. You literally get the best of both worlds, climbing power and cruising economy. Section 3. Inside the governor system. Let's open up the cowling and look at the mechanical heart that makes this constant speed possible. This is where the magic of mechanical automation actually happens. Inside the governor system, there is this incredibly delicate balance of forces. The governor responds to RPM changes by balancing the outward centrifugal force of these spinning L-shaped flyweights against the inward tension of a speeder spring. And that spring, it's controlled directly by your prop lever in the cockpit. This physical tug-of-war moves a central pilot valve, up or down, which then directs high-pressure engine oil either straight into the propeller hub or drains it back out to the engine sump. Let's look at how this plays out dynamically. Picture this: you pitch the nose down. The plane speeds up, and suddenly the prop is rotating too fast, an overspeed condition. Instantly, those flyweights spin faster and are thrown outward by centrifugal force, pulling that pilot valve up. This opens a line sending high-pressure oil from the sump straight into the propeller hub. That oil literally forces the blades to a high angle of attack. This creates more induced drag on the blades, making them harder to turn, which beautifully slows the engine RPM right back down to your selected normal speed. Now, what if we do the opposite? You pull the nose up into a climb, and your RPM drops. We have an underspeed condition. The flyweights lose centrifugal force and fall inward. This pushes the pilot valve down, opening a path to drain oil out of the hub and back to the sump. A heavy spring inside the propeller hub takes over, forcing the blade to a lower angle of attack. Drag decreases, the blades become easier to turn, and your engine RPM dynamically speeds right back up to equilibrium. It's a perfectly self-correcting loop. Section 4. Cockpit controls engine stress. Let's jump into the pilot seat. Moving up to a complex aircraft means you aren't just pushing a single throttle lever anymore. You're managing throttle and propeller levers simultaneously. Now, you might be wondering, why do we even need a manifold pressure gauge in something like an aero? In a fixed-pitch Cessna, your RPM gauge tells you exactly how much power the engine is making. But remember, the aero's governor maintains a constant RPM no matter what you do with the airspeed or throttle. Because the actual RPM is masked by the governor, we absolutely must monitor the fuel and air pressure being shoved into the engine's intake manifold. That manifold pressure gauge is telling us exactly how much power our throttle is commanding, completely independent of how fast the blades are spinning. And this brings us to an absolutely crucial point: the sequence of your levers. For any given RPM, there is a maximum manifold pressure you must never, ever exceed. Think about it. If you force too much fuel and air into the cylinders while the prop is set to a low RPM, meaning the blades have a high angle of attack and are fighting massive drag, the engine is trying to work incredibly hard, but it physically can't spin fast enough. This causes intense, dangerous cylinder temperatures and catastrophic internal stress. So, you must memorize this strict sequence. When increasing power, push the prop lever forward first to increase RPM, then push the throttle. When decreasing power, pull the throttle back first to reduce pressure, then pull the prop lever back. Keep the RPM high before you feed it pressure. Section 5. Handling propeller malfunctions. A good aviator is always prepared for the unexpected. So how does this mechanical system behave when things actually go wrong up there? Well, if you lose engine oil pressure, the propeller hub empties out. Without oil pressure fighting it, that spring inside the hub immediately snaps the blades to full low pitch. This will result in a dangerous engine overspeed condition. On the flip side, what if the speeder spring inside the governor breaks? All tension is gone, the pilot valve slides up, oil floods the hub, and forces the prop to a high pitch, giving you a very low engine speed. And finally, never forget that your engine-driven magnetos are connected right to the crankshaft. If the propeller seizes and stops spinning entirely, those magnetos stop turning, and they will literally stop igniting the fuel-air mixture in your cylinders. And there you have it. By deeply understanding the aerodynamics of thrust, the geometry of slippage, and the elegant oil-driven mechanics of the governor system, you are no longer just a passenger pulling levers in the dark. You know exactly how the machine thinks, how it breathes, and what it needs from you. So the question is, with all this knowledge in your toolkit, are you ready to truly master the aircraft and take the controls?